I am Professor James Elias, and this is a lecture series titled An Inductive Summary of Physics. The purpose of this course is, number one, to understand the essentials of known physics. And I'll be going through this without the technical mathematics. In later lectures, I will actually go through and prove physics through induction, through its observational logic required to actually understand and know that the conclusions are true. But that will require significant mathematical detail at times. This class will not include that. So our purpose is only to understand these essentials of physics. Even if we don't necessarily have the proof of everything in detail, we will often be proving it through inductive logic, and we will often be understanding it enough to know that it is indeed true. And this leads us to the second purpose of this course, which is to understand the scientific method, that is, the inductive method. Science functions primarily by drawing conclusions from observation. But, as we will find, observation on its own is not enough. We need a particular method, and only philosophy can give us this method, a proper method of generalizing from our observations, of moving from observations to particular conclusions. We also need a particular consistent method to do good science, to know when we've actually proven something, and to know when something is only a hypothesis or perhaps just completely arbitrary and has no evidence at all for it. By going through physics in the discoveries of physics in roughly the historical order, understanding an essentialized history of physics. This won't exactly be a history, but we'll go through some steps that are similar to the history, and we'll go through steps by which these scientific principles could have been discovered and proven. So by doing this, we're going to be understanding the inductive method in this class. Those are the two purposes of this class. Now, before we dive into the physics itself, let me give you an introduction to my view of scientific induction. Science is a process of proving things by induction, by forming ideas from observation. As a result, there are specific rules we must follow when trying to genuinely learn science, when trying to actually understand the steps and observations which allow us to know that the conclusions are true. Number one, the first principle of induction that we'll be learning in this class. We'll be learning it by demonstrating it over and over again. Number one, we can only ever gain ideas from observation, nothing from faith or say-so. In this lecture, we will only ever establish ideas from observation. For example, I'm not going to just tell you that the Earth is a sphere and then you have to write that down and memorize it. I will prove it by showing you the observations. So the idea is that we won't literally be going outside and doing these observations, but the idea is that if the observations I present to you in this class are true, then it then follows that the conclusions are true. That is the hope of this class. So, principle number one, ideas can only be gained through observation, never by faith or say-so, which are basically, faith and say-so are basically the same thing. If I just tell you, first it's Mercury, then it's Venus, then it's Earth, then it's Mars, that's the order of the planets. If I just say that to you, I haven't really proven anything. I haven't given you the evidence to think that it's true. So that's not really science. Most classes will not teach science scientifically in this way. They'll teach it the same way things are basically taught through faith. But this is a science class, so we will not be doing that. This is a serious class where we are actually trying to understand the principles, not merely memorize and regurgitate them. Number two, second principle of induction we will be learning over the course of this course. Observations on their own are not enough. Our observations must be integrated, must be put together in the context of our earlier knowledge. Scientific knowledge is hierarchical. What this means is that each idea rests on the progress of previous ideas. The most basic thing you can think of here is that multiplication in mathematics relies on addition. If you don't understand addition, there's no way you're ever going to understand multiplication. And there's no way whoever came up with multiplication, there's no way they could have discovered it and proven it for themselves without first learning addition. And what we will find is that science is like this. So in this lecture, we will only ever establish ideas which can currently be proven in the current context of our knowledge. For example, I can't just come in and tell you, the moon causes the tides. The moon pulls on the water. It does. All of this is true, by the way. The moon pulls on the water, and that makes the water rise up. There's no way, based on your current context of knowledge, unless you have lots of scientific knowledge in physics already, there's no way I could just say that to you and you know that it has to be true. We need a vast amount of prior knowledge. Like, you have to understand when the tide goes up, when the tide goes down. You'd actually also have to understand the mathematics involved. You have to understand the exact way that Newton proved that each bit of water was attracted to the moon and the earth, and the place that water ended up is a combination of those two forces. You'd have to go through those details to really prove it. And in order to go through those details and prove it, you'd have to know everything Newton did at the time that he proved that the tides are caused by the moon's gravitational pull. So as a result, we have to go in roughly a historical order, in some kind of order of discovery, because otherwise our observations are not going to do us any good. If you look at something but you don't have the knowledge to understand what you're looking at, you can't come to any new scientific conclusions. Okay, so that's the second principle that will guide us on this journey. Principle number 3. This actually leads us to principle number 3. Observations themselves actually depend on an earlier context of knowledge. The only way a scientist thinks to make a high-level observation is because his prior context allows him to make that observation. And his prior context also allows him to see that the observation might tell him something. One example of this is the following. A lot of people during Galileo's time, as you probably heard, thought that the Earth was at the center of the solar system and that the sun and planets went around it. Galileo, of course, thought that the sun was at the center and that the Earth and planets went around it. To disprove the old theory, to disprove the idea that that everything's going around the Earth, Galileo actually looked at Venus very closely with his telescope. And he found that the way the sun illuminated Venus, the sun, sometimes only part of Venus can be seen because the sun's only illuminating part of Venus. These are called the phases of Venus. Galileo was motivated to look very closely at the phases of Venus because he found that the way Venus was lit up during different parts of the year was consistent with his theory that the sun's at the center and inconsistent with the commonly held theory that the Earth was at the center. So you can see that without the hypothesis that the sun is at the center, Galileo would never have thought to make this observation. We have to talk about, not only do we have to talk about how observations lead to ideas, but we also have to understand how certain ideas lead to observations. It's only through a process like this that we're going to understand how physics was actually derived from observation. And because observation is not enough, we have to go in this particular order for the observations to make sense. And in this way, we're going to, again, understand these two aspects. We're going to understand the essentials of known physics, and we're going to go all the way from the ancient Greeks, hopefully to the modern day. And we're going to understand how the scientific method works, the inductive method. Okay. Specifically, the aspect of the inductive method that we will be understanding is Leonard Peikoff's theory of induction. Leonard Peikoff, who was a philosopher, came up with a certain theory of how induction works. And he, in my view, solved part of the problem of induction. And this series can be thought of as applying that part of his solution to the problem of induction to the systematic proof of science. And although this won't be a rigorous proof at all times, this will give you a sense of what a rigorous proof will look like before, in later series, I will actually prove math and science step by step. Math and physics step by step. Okay. To know something, you have to know all the knowledge which is hierarchically prior. We already went over this. I think we can skip it. I already said that. Okay, let's begin with the actual content. Let's start with our first integration. Each of the modules in this course, each of the sort of discoveries will be called integrations. The reason we call it this is because science is kind of this continuous flowing process of constant growth. So as a result, it's kind of hard to say when one discovery ends and another begins. And the way I've done it is whenever we reach some kind of essential conclusion, that's when we sort of form a stopping point. And and then sort of integrate. That means to put together everything we've learned so far and sort of coalesce it into one conclusion that we can easily write down and move on. So how did physics get started? Okay, before we do this first one, so here's where the class really begins, the physics content of the class. Before we start, we have to understand so that we don't bring in any unproven assumptions. We're going to start from scratch. I don't want you to use anything you learned on the Discovery Channel. I don't want you to use any ideas that you heard from somewhere, but you don't actually understand the proof of. So to do this, I invite you to put yourself into the shoes of maybe some ancient Greek, maybe even before what we usually think of as the ancient Greeks, back when they just didn't know anything. They were practically cavemen. They don't even know, for example, what the cause of the seasons are. They just know, hey, sometimes it's hot, sometimes it's cold. When it's cold, it sucks. We run out of food, people die. What can we do about this? And so this forms the motivation for our first investigation. Some seasons are good for planting crops, some aren't. If we can understand what causes the seasons, we can better prepare for them. The sun's light, we know, warms things up. In addition, the sun travels in a different path during the day, sometimes staying out longer and sometimes being out shorter. Let me see if I have a picture of this. Okay. This is something that, look at this picture. So this is something that people would notice is in the colder months, in the colder times, this is before they have the concept of year, right? Because you don't have the concept of year until you have the concept of seasons. So I'm just making sure that device is still working. You don't have the concept of a year until you have the concepts of seasons, although they kind of have concepts of seasons. There's the hotter times, which are the winter, and the colder time, or there's the hotter times, which are the summer, and the colder times, which are the winter. And they notice that the sun moves in the sky, tends to move in the sky higher during the summer and lower during the winter. In addition, the sun is out for less time during the winter, and it's out for more time during the summer. So you're probably already forming a hypothesis, okay? Now, here's something to remember. People don't know that the Earth is a sphere. People don't know, they don't know that the Earth is going around the sun. They don't know any of this. They all they know is what they can see. They just notice these trends. So I really want you to start this class by getting rid of everything you think you know. And I don't mean that in a sort of skeptical way, like you can't really know anything. I mean that in a way where we're going to start over. We're going to only build our knowledge on things that we really understand from observation. We're going to put those observations together piece by piece and move forward only on things that we understand. Okay, so this is something that perhaps the older people in the tribe would be able to remember and notice. You can see that I took this picture from the internet because, cavemen wouldn't have houses of this kind. But they would be able to notice this pattern, and so they would form a hypothesis. Since the sun warms the earth, and the sun is out for different durations at different times of the year. Sometimes it's out longer, sometimes it's out colder, and it seems to go in a pattern. Is it the case that the amount of time that the sun shines on the earth is the cause of the seasons? Okay, so maybe the reason it becomes hotter at certain times is because the sun is out longer during those days. Maybe the summer is just caused by the fact that the sun is out longer at that time. Maybe the winter is just caused by the fact that the sun is out for less time during those days. Okay, so I have made up a particular person, a particular historical figure. We don't know who figured this out. This is a prehistoric discovery. Some kind of nameless genius figured this out. And almost every culture did figure this out in one way or another, and at least that I know of, and they all probably had their own nameless genius who figured this out. For the Greeks, I'm just going to call him Anthropocleitus. Okay? So he's our fictional first scientist. Okay? So here's what Anthropocleitus does in order to test this hypothesis that it's the amount of time the sun hits the earth that causes the seasons. So first what he does is he records in a book the daily temperature, okay? And he's going to do this just by feel, okay? He's going to go out, he's going to say, it's kind of hot. He doesn't have a thermometer, right? So he's just, it's kind of hot. Then he'd say, today it's hot. It's just normal hot today. Not kind of hot. It's normal hot. Then, dang, today's real hot. Okay? And so maybe he's able to write this down and get some sense of temperature trends as the days go on. Each day, he's also going to record the amount of time that the sun is in the sky. Okay? Maybe he can do this with an hourglass, which means he takes, basically, that's a fancy way of saying, he'd take a bucket, put sand in it, poke a little hole in the bucket, and then let the sand dribble out. And every time the bucket runs out of sand, he just puts the sand right back in the bucket, and he counts how many buckets of sand run through per day. And he's going to find that, sometimes the days are getting longer and longer and longer until they reach a longest day, and then they start getting shorter and shorter and shorter. They go in cycles. And then they start getting shorter and shorter until we reach the shortest day. And then the days begin to get longer again, okay? What he's also going to do, he's going to record the highest angle in the sky reached by the sun, okay? And here's how he's going to do that. Here's how he can measure and record that. What he's going to do, you don't need to worry about the tangent part. The sun is shining down on his stick, which the Greeks called a gnomon. As far as I know, it just means stick, but it means stick meant to measure the sun, okay? And so basically, the longer this shadow is, the lower the sun is in the sky. You see that? And so if the sun is completely overhead, which happens in some places in the earth, but it doesn't happen in Greece, if the sun's directly overhead, the shadow will, of course, be nothing. But like I said, that doesn't happen in Greece. Even when the sun reaches its highest point in the sky, it still won't be directly overhead. Nowhere in America does that happen, and nowhere in Greece does that happen. either. So basically, but nonetheless, when the sun reaches its highest point for the day, that is the shortest shadow length for the day. And Anthropocleitus could record this. Now, what Anthropocleitus is going to find, let's say he does this for many years. He's going to observe that the longest day, the day where the sun is out the longest, is always the day where the sun reaches its highest point in the sky for the year. You can see again, during different parts of the year, the sun will take different paths. And on the longest day, that is the arc that the sun takes, which is highest. And so again, on the longest day of the year, this is the day where the sun achieves its shortest shadow length when it reaches its highest point. The shortest shadow length for the whole year. Okay, so, and again, that is also happens to be the longest day. However, something a little weird happens. So you'd expect that to also be the hottest day, right? If Anthropocleitus' hypothesis is right, then you'd think, oh, well, it's the longest day, sun's out the longest, so that's going to be the hottest day, right? I mean, or maybe if it's not that, then maybe our hypothesis is wrong. Well, it's not, it doesn't work exactly like that. What Anthropocleitus finds from keeping track of all of this in his records is that the hottest day of the year tends to trail behind the longest day of the year by about 60 days. That's pretty weird. And the coldest day of the year tends to trail about 60 days behind the shortest day. And upon thinking about this, Anthropocleitus realizes that this actually just confirms his hypothesis. And the reason is because things don't heat up or cool down all at once. If you put your hands near the fire, you're not immediately relieved from the cold. It takes a while for your hands to warm up. If you take your hands away from the fire, it'll take a while before they start to get cold and uncomfortable again. And so what Anthropocleitus realizes is that this process of heating up as the days get longer, it takes a while, and the process of cooling down as the days get shorter, it also takes a while, about the same amount of time. As a result, Anthropocleitus is able to conclude that the amount of time the sun shines upon the earth is the cause of the seasons. Okay? Now, this is only the first integration, but what you will find is that it will serve as a foundation, a small but very sturdy foundation on which we build further observations and further reasoning steps as we continue our journey. Okay? Now, before we continue the journey, now that you've sort of seen a one of these integrations and how we do it, how we go through it, I'm going to show you the MQIC method. Okay? Each of our integrations, now this is a general note. This isn't a physics, this isn't one of our integrations in physics. This is just showing you more about how this class will proceed. In order to stick to those three rules I showed you above, remember our three rules. Let me show them to you again. Number one, you can only gain ideas from observation. Number two, your observations have to be integrated with your prior knowledge in order to come to a new conclusion. Knowledge is hierarchical, in other words. Each piece stacks on top of each other piece. And number three, observations actually depend on your prior context of knowledge. Okay? In order to stick to these three rules, each of our integrations in this class will proceed in 4 phases. Okay? First is the motivation phase. You'll notice. And so in the motivation phase, we will always cover what is in the discoverer's prior knowledge. What is it that the discoverer knows that allows him to see that this particular thing is worth investigating. Okay, in the case of Anthropoclitus, he wanted to know the cause of the seasons because there were harsh winters, and during the summer, that's a good time to plant crops. So he wanted to know how the seasons behaved. Okay, the purpose of science, and this is a general thing we have to understand, if we're going to be doing good science, if we're going to be doing science that is actually rigorous, we have to understand the purpose of science. We need to conduct science in a way that is consistent with its purpose. And science has no other purpose but to improve mankind's condition here on Earth. There's a special phrase, there's a special scientific phrase that scientists use, real scientists anyway. There's a special phrase that real scientists use to describe research that has no chance of improving the human condition. Can you think of this phrase? What does a scientist call research that can't improve the human condition? That's called a waste of time. Scientists call this a waste of time. That is the technical term for it. We need to understand part of the context of knowledge, part of the stuff that is hierarchically prior to a discovery, is the knowledge that investigating this particular thing is worth discovering, is worth thinking about, is worth spending time on. Part of this is also knowing, do we even have enough knowledge to conduct this investigation, or do we not know enough right now to try and understand this? If the answer is no, if you don't know enough to try and understand this, then you can see that the investigation is not motivated. You can see that there is no reason to conduct the investigation because there's no reason to think you'll find anything out. For example, if the ancient Greeks, tried to figure out quantum mechanics, tried to figure out the structure of the atom, well, first of all, they would have no reason to try and do that because they weren't even really aware of what atoms were. They kind of had a theory of atoms, but it was different from the actual theory of atoms. So they would have had no reason to do that. And so you can see that by enforcing motivation, by making sure that we always account for motivation in a logical way, you can see that the motivation phase allows us to adhere to proper inductive logic. Okay, the next phase is called the question phase. And by the way, every single one of our integrations will contain all four of these phases. Okay. In the question phase, we will always present the question that the investigator is asking as he conducts the investigation. Or we can put it this way, how the discoverer's prior knowledge allowed him to embark on a given investigation. Okay? A question will always take everything that you know so far, and a question will always take the ideas that you know so far and sort of frame them in a way that allows you to discover new ideas. Okay? And here's the thing. It's possible to frame your prior knowledge wrongly. It's possible to ask an incorrect question. It's possible to ask a question that contains invalid assumptions. So the classic example of this is when someone asks, this was an ancient Greek thing, I think. This is something the ancient Greeks used to joke about. They'd ask the question, have you stopped beating your wife? And so there's no way to answer this question, right? The question is wrong, or at least the question contains an unproven assumption. The assumption, of course, is that you were beating your wife to begin with. And if you answer the question, the only thing to do is to reject the question. If you answer the question, you're screwed either way. Because either you were beating your wife or you still are. So questions can be wrong. Questions can contain invalid assumptions. One example of this is that what we'll find, the Greeks at one point asked the question, why are the stars and planets eternally moving? Or why do the stars and planets move eternally? That's a question they would ask. Because what they found is that when things move here on Earth, you slide a rock across the ground, motion always tends to stop. When something moves, it kind of slows down. That always tends to happen. Whereas in the heavens, things are just moving. And they just keep moving. And so they say, what's different about the stars and planets that they are in eternal motion? And it turns out this question contains within it a certain invalid assumption about the way motion works. And so as a result, so long as the Greeks were asking this question, so long as the Greeks were thinking about motion in this way, that there's just something different about the heavens and that the earth's one way, the heavens are another way, and it's just different somehow. We just need to figure out what that difference is. As long as they were framing the question that way, they were never going to get anywhere. Because they were reasoning from an invalid assumption, that there's something fundamentally different about the motion of the heavens and motion down here on Earth. They just assumed that was the case, and it turns out, they had no reason to think that. That was just an invalid assumption, basically. And so even though so as a result, in general, a question has to be proven in the same way an answer does, because a question brings assumptions with it. A question always represents some sort of integration of your prior knowledge. And so before we answer a question, we have to explicitly identify it in our process of induction before we answer it. Okay. Now the third phase is, I think, the phase that people tend to focus on, and rightly, but you need the other two phases. You need those first two phases for this phase to mean anything. This is the investigation phase. And the investigation phase is the observations and reasoning steps which prove new knowledge in the discoverer's existing context of knowledge. Okay, so for example, we just saw Anthropocleitus. We just saw him prove that the sun is the cause of the seasons. Well, what did he do? He made some observations, right? And he reasoned from prior knowledge. It was really basic prior knowledge, but he did reason from some prior knowledge. He reasoned from the idea that the sun heats stuff up, right? That's basic knowledge, but you need to know that before you can talk about this. Like an infant couldn't have done what Anthropocleitus did. You need to learn that the sun heats stuff up first. You need to know this general sort of knowledge that sometimes the sun is in the sky longer, sometimes it's in the sky less time. So you can see during the investigation phase, we are conducting both observations and reasoning steps from our prior context of knowledge. Okay? And finally, there is the conclusion phase. And this is when the new discovery is integrated, that is put together. It's connected with the other things that you know. It's integrated into your knowledge state by stating it briefly and clearly. That's very important, to state it briefly at the end. And so whenever we come to the way I've done this is that each integration will reach a conclusion once the object of the motivation is satisfied. Once we have achieved what we originally set out to gain in the motivation, that is when we will consolidate our findings into a brief conclusion. So what you might consider doing as we proceed through this journey through the inductive logic of physics, you may want to come back to this early part of the video where we talk about these principles in action. I'll be making references to the principles of induction as we proceed. I'll be making references to them and showing you like reminding you how these different things work, but you may consider coming back to this. And I already said this, but I'll say once again, these three rules and 4 phases, the 3 rules of induction I've given, and the 4 phases for adhering to them are part of Leonard Peikoff's theory of induction. I'm trying to put that part of Leonard Peikoff's theory of induction into practice. And so I think this constitutes a demonstration of what inductive hierarchical thinking looks like. Okay? So with those philosophical preliminaries, and it's important that we keep those philosophical preliminaries in mind as we proceed through this so we can learn the proper method of science. With those in mind, let's continue our story. Number 2, the phases of the moon. So we just proved earlier, we proved the cause of the seasons, and now we will try to understand the phases of the moon. First, the motivation. We have seen that knowledge of the heavens can teach us about what happens here on Earth, and it allows us to make informed decisions, in this case about when to plant crops. Now, it's observed that the moon takes on a different shape on different nights and days. So we now have a motivation to understand these different shapes of the moon. Let me show you what the different shapes of the moon look like. These are called the phases of the moon. You can see sometimes it's very skinny, and I'm sure you've seen this when you go outside. On different nights, the moon will have a different shape. Okay, sometimes we have a full moon. Sometimes we have, you might call this a half moon, but it's called a quarter moon because the moon's a sphere. And we're going to discuss how we know the moon is a sphere in a moment, but it turns out the moon's a sphere. You probably already knew that, but the reason I'm saying this is to always make sure we don't assume anything until we've proven it. So for now, I'm gonna that's sort of a debt I've given to you. I'm gonna have to pay you back with evidence. I'm telling you the moon's a sphere. I'm gonna have to prove that to you eventually, that the moon's a sphere. Okay, but we call this a quarter moon because you can only see a quarter of the whole sphere. Anyway, so he's got these different shapes, right? So, people are motivated to understand this because they can see that the heavens control the earth in a certain way. And if you look historically at how this tended to happen, what you'll find is that you can see that a lot of times this gets blended with a lot of mysticism. You'll see that the priests and shamans and people like that, they would combine their oogity-boogity non-scientific nonsense with actual observations of the heavens. And so this is where astrology comes from, the idea that the positions of the stars can tell you something about your future, that sort of thing. It comes from there. But behind all that non-scientific ooga-booga is a kind of real motivation. We've seen ways that the heavens do control the earth. So by understanding the heavens, we learn more about this universe that we inhabit, and we can learn more about how to act in this universe. And so it's this kind of motivation that legitimately drove the curiosity of early mankind. And what I'm doing in this story is I'm simply stripping it of the ooga booga and focusing on the part where people are observing and reasoning. Okay, so first motivation is, we're interested in what's going on with the moon. So here's the question phase, what is the cause of this change in the moon's shape? So here's what happens. Let's just do a little bit at a time. What we find is that the moon grows and shrinks in a 28-day cycle. It takes 28 days to go from this to this to this to this, blah, 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 until we don't see the moon at all. And then we start to see it, the other side of it begin to become light. Okay? Now, one hypothesis someone might come up with is they say, well, the sun lights up the earth. So maybe the sun lights up the moon, but it only lights up part of the moon, And so as a result, maybe this change in the shape is caused by the fact that the sun is only lighting up part of the moon. So here's what that would look like. Okay, so here's the sun. Here's us on the earth. Ooh, why is the earth flat? Well, go outside. It looks flat, right? We don't have any evidence the earth is a sphere. It is a sphere. I'm not saying that the earth is flat. I'm saying that at this point, there's no evidence that the earth is a sphere. Okay, so that's how we're going to draw it until we prove that the earth is a sphere. And you're going to see that we're going to prove that pretty damn quick. All right, so anyway, let's proceed. You can see that the sun is lighting up the side of the moon, which is facing the sun, of course. Now, when you're here, look at this. When the moon's kind of close to the sun in the sky like this, you don't see the moon at all. And this, okay, then when it's a little further away, you can see that, what's this guy going to see? He's going to see this part lit up. So this is a crescent moon. Here's a crescent moon right there. You see in the upper left, that's a crescent moon. So as the sun, we only see a little bit of the lit up part, right? Then here's the quarter moon. You can see half of the moon lit up. There it is. Okay. Then this is called a gibbous. This is when you can see the majority of the moon lit up. It's a funny sounding word, gibbous. Where's a gibbous? Here's a gibbous right here. Most of the moon's lit up right now. Or most of the half that you can see is lit up. Okay. And then a full moon occurs when the sun and moon are in opposition, because the part of the moon getting lit up is completely exposed to the observer. And so there's your full moon. Okay. Now, they take the position of the sun and the position of moon into account over the course of many days. And they find that indeed the position of the sun and moon is always consistent with these predictions of what causes the phases. Okay, this hypothesis is always consistent with what is observed. And so we see conclusion. Since the phases of the moon always vary with its relative position to the sun in the sky, we know that its phases are caused by the angle at which the sun's light strikes the moon. Okay? And so now we know the phases of the moon. Okay? Slow and steady progress. Next, people are going to wonder, and this is our Greek hero Anthropocleitus. He's a made-up guy. Whoever this nameless genius was who figured out the daily path of the sun, we honor him or her with the name Anthropocleitus. Okay, so first, so number 3, integration 3, the daily path of the sun. The sun, here's our motivation. The sun controls night and day, so understanding its motion might teach us important things just about how this world works. So one way you can ask this question is what is the sun doing when it goes under the earth? It looks like the sun is going through the sky and then it descends beneath the horizon. Now what's it doing after it, once it goes beneath the horizon, what's it doing? Okay, so here's one. So now, when Greek astronomers measure the speed of the sun, they find that it goes 15 degrees per hour through the sky. Every hour, they find it's consistent. It's going in this pattern you can see on my screen. Okay. Always tilted. Not always tilted. But in most parts of the world, including Greece, it's tilted like this as it goes through the sky. And what Anthropocleitus does is he assumes that the sun continues its 15 degree per hour journey once it goes beneath the earth. And when he makes this assumption, he is able to successfully predict the time and location of when the sun rises again. He's able to predict the time and location on the horizon for when the sun will rise again. And so he's able to reach the conclusion. The sun travels in a circular path through the sky over a 24-hour period and beneath the earth. That wasn't a grammatical thing I just said. The sun travels in a circular path through the sky and beneath the earth in a 24-hour period. Okay, now we're really cooking. Now we're going to get to something pretty interesting. So Anthropoclitus, in my little story, he founds the elders of the heavens. I made this up, okay? This is not the actual history of Greece. But imagine that there's this ancient order of scholars, of philosophers, and their job is to just watch the heavens and to try to understand things about the heavens so that we can continue to learn more about this world we live in. Another thing I'm gonna note in order to motivate investigations of the heavens even more is that what people were able to do at this point is use the sun as a clock and use the moon as a clock, use the phases of the moon for telling time. And by keeping track of different positions and of different stars and planets, I'm not going into the details of this, but by keeping track of the positions of the stars and planets, people are able to navigate and people are able to keep track of consistent time so that they know exactly when to plant the crops based on when the next season is likely to occur and all of this sort of stuff. So learning more knowledge about the heavens has proven valuable. And so we have this ancient order of Greek scholars who I made up, but they had something like this. People were interested in learning more about the heavens. And as I've already said, a lot of times these were religious orders. A lot of times these were, they thought they were learning about the sun god and his various moods and behaviors, and they were studying that. And, it was a combination of legitimate scientific investigation and just sort of, superstition and not really understanding quite the way the world works. But again, what I'm doing is I'm stripping it of its superstition and unproven mystical aspects and going only with those parts of the history that were scientifically substantiated, that were discovered by these ancient peoples. Okay? So anyway, elders of the heavens, you got these men, they're watching they're watching the sky, right? And let's say that one night during a full moon, one of the elders, he's chilling out there, probably with a beer. He's chilling out there. He's just watching the full moon. That's his job. They at least got one guy watching the sky at any one point, just making notes about anything new he sees. And he sees something truly exciting. It's a full moon, but then suddenly the moon starts getting shaded. He starts noticing a little shading in the corner, but after about just an hour, it starts looking like this. Now, you might be saying to me, James, why is this a big deal? The moon, you already told me the moon changes shape, so I don't get it. What's the big deal? The big deal is that it usually takes about 5 days for this much shading to occur. In addition, I don't know if the first guy would have noticed this right off the bat, but maybe he would have because, these people were obsessed with looking at the sky, so they probably would have noticed this right off the bat. Notice the direction of the shading. It's a circular shading, but it's sort of shaded in this direction. Okay, let's go back. Here it's shaded in a different shape, you can see. Let's look at the gibbous. You'd call this a gibbous because most of the moon is still there, but it's like it's got a big bite out of it. Here, the gibbous shape is different. It's curved in the other direction. It's a convex curvature instead of a concave curvature, okay? So something different is happening. Something very different is happening. And eventually, this shadow consumes the entire moon. It only takes, and again, the biggest deal about this is that it takes only a couple hours, where usually To go from a full moon to a gibbous moon takes days, but this just took a few hours. So whoever the guy is, he's waking people up, he's waking up everyone. Look at the freaking moon. Some people are like, I don't get it, like it's the moon. But eventually, but the elders of the heavens do notice that something is very awry. It's supposed to be a full moon tonight, and we have a gibbous moon, or whatever the hell this is. Something totally different. Once the moon is entirely consumed by the shadow, it turns red. Right? Now, here's where we have to applaud the Greeks here. I think most cultures probably took this to be the end of the world, or God's mad at us, or like war is coming because, the moon's red and red looks like blood, and, blood shed happens in war, so maybe war is about to happen. Maybe it's just people are going to get pissed at each other and start fighting soon because the moon's red. Duh. That kind of, I'm making it sound really silly, but I think the temptation to just say, I can't explain this, so it must be, whatever, to just jump to some kind of explanation of this before there's any evidence, is very tempting, and the Greeks didn't do it. Because, by the way, the Greeks never explained why this is red, why the moon gets red. Yet they still were able to explain what the hell is happening right now. So anyway, the shadow continues its motion, and eventually the moon starts to emerge from the shadow like this. So first it was sort of taking up this side, then it takes up the whole thing, and the moon gets it red, and then it starts moving away from the moon, and the moon emerges from the shadow. So what the hell is going on? Well, before we talk about what the hell is going on, I'm going to point out that this observation would not be possible if it weren't for our prior knowledge of the moon's phases. If it weren't for the fact that we already know that the moon goes in a certain pattern, then we never would have noticed that this was anything different. This red thing would have been different, but this particular shading that led to the red thing, that wouldn't have been noticed. People would not have noticed that something different is going on here. They just would have noticed the moon was red at some point, they'd get scared, and that would be it. Right? So this allows you can see that not only are our conclusions based on prior knowledge, but our questions can be based on prior knowledge. The only reason this occurs to us as being an interesting thing to investigate is because of our prior knowledge. We can see something new is going on, and this leads us to the question, what is the cause of this unusual shading of the moon? Okay, and here's what the nameless Greek genius, let's call him Anthropoclitus again, let's see what he came up with. Since this happened during a full moon, perhaps it was caused by the earth shading the moon from the sun's light. Perhaps the earth is getting in the way. I've made this too big. Let's zoom out. Okay, take a look at this. Let's make it bigger. All right, take a look. So the sun is shooting its rays out, and the earth is, and right now it's a full moon, right? So the sun and the moon have to be in opposition. But maybe the earth is blocking the moon from the sun's light. Okay. Now, this leads us to a question. Why don't we just have an eclipse during every full moon? Well, there's a way to explain that too, okay? So here's what might be going on. Usually, perhaps, the moon is a little off to the side of the shadow. Yet, here's the thing, you'd still basically see a full moon here. Maybe it wouldn't be 100% full, but it would be so close you wouldn't notice, okay? But every once in a while, it turns out it's like every 2 years or so, you'll see the moon will actually be enveloped in the Earth's shadow, and that's when an eclipse actually happens. Now, this leads us to a sort of scary idea here. What it means is that the size of the Earth is small in comparison to the distance between the sun and Earth and the Earth and moon. Let me show you what I'm trying to say here. Get to finally use my iPad. Take a look at this. Okay. Let's say the Earth, here's the Earth. Remember, we don't know the Earth's a sphere, so it's big, right? Let's say the Earth's real big like this. Here's the moon, here's the sun, okay? Sun, let's give the sun sunglasses to protect its eyes from, the sun. They always depict the sun with sunglasses. There we go. It's a little demonic because I can't draw. So anyway, notice how this distance is roughly on par with the size of the Earth, and then this distance is also roughly on par with the size of the Earth. If this were the case, the moon would get blocked by the Earth every time we had a full moon, right? Or I'm sorry, the sun's light would get blocked by the Earth every frickin' full moon. Okay? That doesn't happen though. It only happens once every 2 years. So what must be the case is that the Earth is actually quite small in comparison to this distance. Let me draw this the way it probably actually is. Okay. Maybe the Earth, I'm going to make it real small, and then here's the sun, and then here's the moon. So take a look. I've drawn it so childishly. Hold on. See that notability is doing me some favors here. So there's the Earth. I keep putting a dude on there so that or a woman, could be Hypatia over here. So, here's so the sun is shining, and you can see if the Earth is small in comparison to these distances, it starts to make a lot of sense that an eclipse doesn't happen all the time. Okay? So, there you have it. We've learned some seriously interesting things here. Okay, so let's take a look. So the sun and moon must be very far away in relation to the size of the Earth. Okay? I mean, at one point, what was his name? His name was Anaxagoras. He was a Greek thinker. He said, dude, guys, I think the sun might be real big. I think the sun might be like as big as Greece. And everyone's like, Anaxagoras, you crazy lunatic. Like, God, like, why are you such a lunatic? And I think they kicked him out of Athens for saying this. Like, we can't have people saying crazy stuff like this. But it turns out the sun's got to be way bigger than Greece, because it's so far away. It's way further away than the furthest place on Earth. Maybe they know about China. I think maybe the Greeks knew about China. Like, think about how you walk all the way to China. It's really far, right? Well, the sun is way further away because look, it's got to be set up like this. Otherwise, we'd have an eclipse all the frickin' time. Otherwise, we'd have an eclipse every single time the moon was above and the sun was below. And it doesn't happen like that. So this stuff must be real far away, even in comparison to the size of the Earth. Okay. Now what we see is that careful observations of the position of the sun during future eclipses always show that, yes, the lunar eclipse will only occur when the sun and moon are in direct opposition to one another. By keeping track of the positions of the sun and moon, by sort of estimating the position of the sun when they can't see it, when it's underneath the Earth, by making estimates of this, they say, yes, the eclipse will only occur when they're in direct opposition. And many Greek thinkers were actually able to predict eclipses because they were keeping track of these positions. They'd say, guys, tomorrow it's going to be an eclipse. And they're like, whatever. And then it happens. And so the Greeks, I think, as a culture, really had a respect for ideas because they could see that these great men, these philosophers, were able to make predictions using their minds and an understanding of this world and universe that we live in. And so we'll state our conclusion in a concise way, and we will say that the lunar eclipse is caused by the Earth blocking the moon from the sun's light. Okay. In our next integration, the Greeks are going to be inquiring about the shape of the Earth. We already know that this eclipse shadow is caused by the Earth. So if we can figure out the shape of the shadow, then we can figure out the shape of the whole Earth. And maybe we would understand something about all lands in existence. This is the motivation to investigate the shadow. So, question number 5. What is the shape of the Earth's shadow? Investigation. By looking at many drawings of different eclipses, we are able to see that the Earth's shadow is circular. So here's the idea here. What the Greeks would do, the elders of the heavens, in my little story, the elders of the heavens would draw pictures of the moon during an eclipse. And so what this would allow them to do is it would allow them to see the shape of the shadow. You can think of the moon as this little piece of film that registers the shape of the Earth in 2D on it. And so by drawing different pictures of the moon and then piecing those different pictures together, you might come up with something like we see here. And so you can see this gives us this shape, which is it's always circular. Okay, so what this might lead the elders of the heavens to think is perhaps the Earth is a circular disk. Right? So we're not there yet. We haven't yet discovered the evidence for why the Earth is a sphere yet. When we go outside, it looks flat, and the shadow is a circle. So maybe the Earth is just a flat disk like this. Okay. But this leads us to our next hero. Our next hero's name is Aristotle, and this is our first historical hero. Let me show you what Aristotle looked like. Here's what Aristotle looked like. Our first historical hero. Here you can see that, you can see in all of these different depictions, he has a very impressive beard. Everyone agreed. Everyone who depicted him agrees that he has this very formidable beard, a beard almost as formidable as his intellect. So here's what Aristotle does. Aristotle is thinking about the shape of the Earth one day, and he's, okay, people say it's a disk, and here's the evidence. And then he realizes, wait a second, if the Earth were a flat disk, wouldn't that mean that the shadow it casts on the moon is usually kind of an oblong shape? If you look at this diagram I've drawn, if the Earth was indeed a flat disk and the sun was sort of canted off diagonally like this, that would produce an oblong shadow on the moon. It wouldn't produce a circular shadow, because when a disk is looked at from the side, it casts an oblong shadow. Let me demonstrate with a circular object. So I've grabbed a circular object here, but when you look at the circular object from the side, you can see it makes sort of an oval shape if you just consider the shape it makes on the camera. So Aristotle looks back at the pictures. He looks back at the pictures of the moon during the eclipse that the elders of the heavens had drawn, and he realizes the shadow is always circular, and it's always a circle of the same diameter. It's always the same size. Well, what's the only shape that casts a circular shadow in every direction? It's a sphere. Now, so the world must be a sphere. Now, Aristotle was already aware of a hypothesis regarding the Earth being a sphere. Pythagoras thought, a thinker who came earlier than, and Pythagoras was a real thinker as well. A thinker who came earlier than Aristotle said that he thought the Earth was a sphere because if you look at ships, if you look at this photo here, when you look at ships as they're going over the horizon, they seem to sort of sink below the horizon in this way. And so Pythagoras was saying that maybe the Earth is a sphere and that this is a ship sort of going around the sphere, like over the hump, you might say. And so as a result, now, so this was just a hypothesis at the time, but we can see that Aristotle has confirmed the hypothesis. And that leads us to conclusion 5. The Earth is a sphere, and all lands and seas rest upon its surface. So think about the enormous amount of progress we've made so far. And this is nothing. This is nothing in comparison to the journey that we will be taking throughout this entire class. But look at what we started. We started without knowing anything. We didn't know when summer would come. Wouldn't know when winter would come. People would just die in the winter. And we've made it all the way to understanding the shape of the entire Earth, to knowing that the Earth is a sphere. And you can see that this is only made possible by going one step at a time, by using the knowledge of previous thinkers to make new observations and integrate our knowledge on a wider level to understand further facts. Now, this leads us to a thinker named Eratosthenes who figured out the size of the Earth's sphere. Let's look at what Eratosthenes looked like. Eratosthenes. Google has helped me a little bit here. We can see that Eratosthenes' hair is not as formidable as Aristotle's, but I think we'll find that his contributions are no less fantastic, at least in the realm of astronomy. In the realm, generally speaking, Aristotle was probably the smartest man to have ever lived. So he overtakes Eratosthenes in that realm and in the realm of facial hair and in the realm of hair in general. So here's what Eratosthenes is thinking. Eratosthenes hears that in the city of Syene, the sun is directly overhead on the longest day. So let me show you. Let's see, Alexandria and Syene, Africa. Both of these cities are in Africa. Okay, so here's Africa. Now here's Egypt right here, okay? Both Alexandria and Syene are in Egypt. So if you zoom in on Egypt here, Alexandria is here on the northern coast of Egypt, and Syene is south of there, okay? Syene is closer to the equator of the Earth, it turns out. And so here's what Eratosthenes heard. He heard that on the longest day, the sun is directly overhead in Syene. Okay, that means that there are no shadows. That's what people thought was really interesting. You know, on the longest day in this city, the sun is directly overhead, so there are no shadows at noon on the longest day. Now, Eratosthenes finds this very interesting because in his city, Alexandria, the sun is never directly overhead, even on the longest day. Even on the longest day, you'll get short shadows at noon at the longest day, but you'll never get no shadows at no point during the year. So Eratosthenes finds this interesting because he realizes, well, Aristotle already taught me that the Earth is a sphere. And so if you think about this, it kind of makes sense. Let's minimize that. If you think about this, it kind of makes sense, says Eratosthenes. Let's say this is the surface of the Earth. Let's say this is Syene. Here's the sun's light. It's coming in, and it's hitting. Let's say we have a stick right here. The stick will cast no shadow in Syene because the light's hitting it straight on. But over here in Alexandria, we have another stick. The light comes in in the same direction. You will have a shadow. Okay, you will have a shadow in Alexandria. So Eratosthenes simply says, okay, this makes sense. The Earth is curved, so it makes sense that at the same time of day, you'd get a different shadow length between Syene and Alexandria. Now, this makes Eratosthenes think about something. He realizes, hey, there's a difference in angle in the way the sun hits these two sticks. Could I use this difference in angle to calculate the size of the Earth? Now, the reason Eratosthenes thought this might be possible is because in general, geometry is able to measure things that we cannot measure directly. A lot of times with geometry, you can set up a kind of diagram like this. And if you remember your geometry class, a lot of times you set up a diagram and then you can solve for angles and lengths that you cannot actually go and measure directly. And Eratosthenes would have been very accustomed to using these methods of geometry. And so he asks the question. What's the question he asks? Let's check. Oops, I've minimized everything. He asks the question, can we use the difference in shadow length between Alexandria and Syene and geometry to measure the size of the entire Earth? The answer ends up being yes. Here's how he achieves it. So what he does first, let me show you what he does first. He gets a man to walk all the way from Alexandria to Syene. So Eratosthenes isn't going to do it himself. He's got better things to do. So he hires a man to use notability for him, since he can't draw either. Or no, that's me. Come on. I'm trying to draw the Earth. I'm trying to draw a sphere, or a circle rather. Come on. It just deleted it. Fantastic. Why is this so hard? He asks as technology does his work for him. There you go. Okay, so here's the Earth, okay? Here's Alexandria up here, okay? And here's Syene, okay? Okay, here's Alexandria, here's Syene. Here is a light ray passing through Syene. You know, if you do things right, you can actually make things straight in notability. There you go. There's a light ray passing through Syene. Okay, so I'll draw arrows on it. Okay, here's the center of the Earth here. Okay, let's make it a little. There's the center of the Earth. Now here is a light ray passing through Alexandria. Okay, and so there's a little shadow here, right? There's a shadow. All right, now check this out. The man that he hires to walk from Alexandria to Syene measures out a distance of 800 kilometers. Okay. Now once the man gets from Alexandria to Syene, what the guy does is he looks down a well at noon on the longest day of the year. This is called the summer solstice, by the way. He looks down the well and he sees that at noon, the sun is able to illuminate the bottom of the well, which proves that the sun is indeed overhead, and indeed these light rays right here are striking Syene directly. Now, at that same time, back in Alexandria, Eratosthenes measures the shadow length at noon when the sun is at its highest. And what Eratosthenes does is he takes an old column. I was going to say a Greek column, but of course they were all Greek. Even though this is Egypt, it turns out this is, it's part of Greece. So the sun is coming in like this, and it casts a shadow. So there's no shadow in Syene. There is a shadow in Egypt. And by measuring this shadow, Eratosthenes is able to see that the sun is striking the Earth's surface in Alexandria at an angle of 7.2 degrees. Okay, so let's return to the big Earth picture. So here we have a 0 degree angle in Syene, but in Alexandria, the sun is striking the Earth at a 7.2 degree angle. Now I'm going to draw an extra line because this is what Eratosthenes does. Okay, draws an extra line. So remember, this is a 7.2 degree angle because, again, that's the angle that Eratosthenes' stick makes in Alexandria by measuring its shadow. Now, what Eratosthenes does is he assumes that these two sun rays, the sun rays striking Alexandria and the sun rays striking Syene, he assumes that they are parallel. Now, this is an assumption, and I'm going to cover this assumption later. It turns out it's an okay assumption to make, but I'm just labeling it as an assumption. Now, what Eratosthenes does is he now knows that the angle in the middle of the Earth, which separates Alexandria and Syene, he also knows that that is 7.2. And this is a theorem in geometry, which is that opposite interior angles are always equal when you have two parallel lines. So he's relying on the idea that the sun rays are parallel, and we're going to have to prove that later, but so long as they are parallel, he knows that the angle from the center of the Earth separating Alexandria and Syene is exactly 7.2 degrees. Okay? He didn't want to dig to the center of the Earth and measure that angle himself. That would take too long. So he used geometry to measure it indirectly. Okay? Now, he's measured a small portion of the surface of the Earth, right? Now, here's the deal. He knows that this 7.2 degrees can be thought of as 7.2 degrees out of the entire Earth's circumference, right? It's just part of the Earth's circumference. And that proportion is equal to the part of the Earth's circumference that he measured, or rather that his man measured. 7.2 degrees is the same part of the whole circle 360 as 800 kilometers is to the entire Earth's circumference. So now it's just a matter of simple proportions to find the circumference of the entire Earth. Now it turns out that 7.2 is 1/50th of 360. It turns out that that works out pretty conveniently. Then we got 800 kilometers over c, over the circumference we're trying to measure. Measuring indirectly, right? That's the power of geometry, is to measure indirectly. We're going to multiply both sides by 50. And we're going to, well, let's just do that. So we got 1 equals 40,000 kilometers over c. Then we're going to multiply both sides by c. And this leads to the circumference is equal to 40,000 kilometers. Eratosthenes has measured the size of the entire Earth using nothing but shadows and geometry. So again, you can see how each step leading to each other step vastly magnifies our ability to learn more. And our ability to learn more, of course, magnifies our power to act in this world. Eratosthenes now knows the size of the entire Earth. Now, unfortunately, by the way, this number was lost to history at first. So Columbus didn't know this number. I think Columbus had, I'm not sure, but I think Columbus had a different number, which was wrong. And as a result, he thought he would reach India much sooner than he actually would. So this knowledge would have been good for anyone trying to circumnavigate the world, but it turns out that it was lost to the man who was trying to find new places in the world. And we find that the Earth's radius is 6,371 kilometers if we do some simple geometry right there. Okay. Now, we have found the size of the entire Earth. And what we will see is that this knowledge ends up bringing the entire solar system into perspective for us. It ends up allowing us to measure the distances and size of our entire solar system. But before we get to that, I'm going to show you something that our next hero, Aristarchus, figures out. Aristarchus. So Aristarchus is interested in figuring out the geometry of the heavens. He wants to know how far away the moon is and how far away the sun is. And so he realizes that geometry is going to allow him to do this. Geometry, of course, allows us to measure things that we normally can't measure. And so what Aristarchus is going to do, let me show you a picture of Aristarchus. Aristarchus of Samos. You can see I've Googled these guys a few times. Aristarchus of Samos also has very impressive hair. I would say this is actually more impressive than Aristotle's hair. So you can see that over the course of this, we will be rating the appearance of the various philosophers and mathematicians and physicists as we go. So Aristarchus wants to understand the various distances. And here's what Aristarchus comes up with. So what's the question? What's the question that Aristarchus asks before we get into his investigation? He wants to measure the angle between the sun and moon. And in general, the further away the sun is, the larger the angle is going to be from the sun and moon. So what can we learn by measuring this angle? Asks Aristarchus. So let me show you what he's thinking. Here's what Aristarchus does. Here's the Earth, okay? Here's the Earth, and here is the moon, okay? And then here is the sun. Let's make the sun big. Look at that. It doesn't know what to do with my childish drawings. Just deletes them. Okay, there's the sun. Here's what Aristarchus does. Maybe we'll move it a little bit. Yeah, there you go. Hey, thanks. Gives me a little... Aristarchus waits until we see a half moon, or rather a quarter moon, okay? During a quarter moon, now there's a problem. During a quarter moon, or a half moon, you know, when you can see half the moon, you know that from the moon's perspective, the angle between the Earth and sun is 90 degrees, right? Again, when there's a half moon, you know that the angle between the Earth and sun, from the moon's perspective, is 90 degrees. So he's able to know that angle by looking at the shadow on the moon, by looking at the phase of the moon on a particular night, okay? Aristarchus then measures this angle from the position of Earth. And it turns out that this angle is 89.96 degrees. 89.96 degrees. Okay. So, it's very close to 90 degrees, which means I haven't drawn this properly, by the way. The picture looks a heck of a lot more like this. And even this is not quite right. But you can see that this starts to look a heck of a lot like 90 if the sun is super far away in comparison to the distance between the Earth and the moon. Okay? So what Aristarchus has already learned is that the sun is a heck of a lot further away than the moon is. Okay? Now, how much further away is it? It turns out that if this is d DEM, we'll call, distance from the Earth to the moon, and this is DES, then it turns out that the distance from the Earth to the sun is 422 times further away than the distance between the Earth and the moon. Okay? He's able to do this using trigonometry. Now, quick historical note. Aristarchus was not actually able to measure this angle very accurately. I have him measuring the angle very accurately. He wasn't able to do that. He also didn't have the trigonometry required to know that this angle meant that this was 422 times bigger than this. But in this development that I'm creating, we're going to cover those geometric facts in the final version of my inductive proofs. We're going to be going over those geometric facts first. So in this story, we're going to pretend that Aristarchus had this measuring ability and he had this knowledge of trigonometry required. The real story is that Aristarchus did figure out all of the math we're about to do, but he just did it with numbers that weren't quite right. But he did end up figuring out all of the major qualitative conclusions that we're about to go through. So anyway, here we have a very interesting discovery, which is that the distance between the Earth and the sun is 422 times larger than the distance between the Earth and the moon. Now, we don't know the distance between the Earth and the moon. We don't know how far that is, in kilometers, in units that we actually can compare to ourselves here on Earth. But we do know the relationship between the distance to the moon and the distance to the sun. And you're going to see that this ends up being extremely powerful knowledge. Okay. Now, Aristarchus is going to use this knowledge to figure out the size of the moon and the sun. He's actually going to figure out their size using geometry. He's actually going to figure out how big these objects are in kilometers. In units we can compare to units here on Earth. Here's the way Aristarchus thought of it. He says, okay, I know that geometry gives me the power to measure things I can't measure directly. Now, the Earth's shadow depends on the size of the Earth, right? The Earth's shadow is not the same size as the Earth necessarily, but it's based on the size of the Earth, right? And the Earth's shadow projects itself onto the moon. We know the size of the Earth. So maybe I can figure out the size of the moon by comparing it to the Earth's shadow. It's a long shot, but let's draw the diagram out and let's see what we can do, right? So here's the first thing he does. Before he draws the diagram out, he takes a certain measurement. He wants to see how much bigger the Earth's shadow is than the moon. We already know that the Earth's shadow is way bigger than the moon. Take a look at this. By drawing all these different pictures, people noticed, the Earth's shadow is larger than the moon itself. And so Aristarchus thinks, maybe I can figure out how much bigger it is. Maybe I can figure out how much bigger it is. And here's what he does. This is absolutely genius. Here's what he does. He watches very closely one night during an eclipse. Now, here's what the eclipse is going to look like. Okay. Let's say that this is the Earth's shadow. Now, you can't literally see the Earth's shadow. You can only see its effect that it has once it passes over the moon. But what Aristarchus does is he waits until the moon, let's say this is the moon. Let's label these. He waits until the moon just barely starts to get shaded there in the end. What he does is he starts a timer. He starts a timer and he figures out how much time it takes for the moon to be deleted. Why does it do that? It keeps deleting it. He figures out how much time it takes for the moon to go from here to here, to be completely enveloped in shadow. Okay? And so he calls that, maybe he'll call that TS, all right? And he finds, let's just say for the sake of argument that it's an hour. It is about an hour, but it's not going to be exactly that. If it takes 1 hour for the moon to be completely enveloped in shadow like this, then what Aristarchus finds out is that it takes 3 hours for the moon to then emerge from the shadow. Let's look at what that looks like. See, after the second hour, it looks like this, and then it gets resized, which I kind of needed to do anyway. And then during the third hour, it gets deleted, and you have to try again. During the third hour, it looks like this, and then beep, it starts, come on. Then it starts peeking out from there. It makes that little sound, beep, and as soon as it peeks out, he ends the timer. And what he finds is that it takes 3 TS, it takes 3 hours, let's say, for the moon to cross through the Earth's shadow. What this means is that the radius of the shadow is equal to, let's call it SH for shadow. The radius of the shadow is equal to 3 times the radius of the moon, because you can fit 3 moons in there. Okay, so now he has a comparison between the size of the Earth's shadow and the size of the moon. And what you're going to see is that this comparison is actually going to help us, okay? This comparison is going to help us quite a lot, because Aristarchus is going to draw the following diagram. Here's the diagram he's going to draw. This is a geometric diagram, and as we've seen, geometric diagrams are actually extremely powerful, because you can draw a situation and then figure out measurements that you ordinarily wouldn't be able to actually measure using the measurements that you have measured. So let's take a look at what Aristarchus draws. Here's what he draws. First, he draws the sun, okay? Then he draws the Earth right here, okay? These are not to scale, obviously. Well, Aristarchus didn't know that because he doesn't know the size of the sun yet. So maybe the sun's only a little bigger than the Earth. Now here is the moon. Okay. Now, what he's done here is he's drawn the Earth. Let's put the Earth a little more like that. And let's put the moon. I guess I made the moon a little bigger. Let's see if I can. I want to get it all lined up. That's actually okay that it's not lined up. So what he's done is he's drawn the situation, the arrangement of these 3 objects during an eclipse. When it's like this, the sun's light, of course, is going to shine like this. Well, it's not that the light is going to shine like that. It's that, let's see if I can, let's try that again. What this represents is that the sun's light is shining everywhere except in this area, because, of course, the Earth is blocking it. The Earth is blocking the sun's light. Let's make that. Let's go like that, okay? So, and then the poor moon is, let's just put a moon in here. Okay, there's the moon. Okay, so, and the moon is enveloped in shadow at a certain point, right? So, here's the situation Aristarchus sets up, okay? Let's actually draw this a little better still. This will pay off if we draw it better later. Or if we draw it good now. One more time. Okay. So, now what Aristarchus does so he's set up a sort of geometric situation right now. Okay. And this situation involves triangles. Okay, so he has this set up so that he has these triangles set up. Okay. Now, the height of this triangle is equal to the radius of the sun, which we're interested in finding out. So we're going to draw that on our diagram. This right here is, of course, the radius of the Earth. And I'm going to put a little star right there because the radius of the Earth is a known number. That's a number that we can use to figure out the other numbers. So maybe we have enough information to figure all of this out geometrically, says Aristarchus. Okay. Now, over here, we're not going to draw the moon. I'm actually going to delete the moon here real quick. And I'm going to put the Earth's shadow here. Okay? The Earth's shadow. Now, the reason that we're interested in drawing the Earth's shadow here, well, you'll see. But basically, we're going to put this radius in here, and I'm just going to write 3. I'm going to write 3 times the radius of the moon. Because remember, the Earth's shadow... Remember how the Earth's shadow is 3 times the radius of the moon? That's how he thought that. And so he's going to put that on his diagram. You'll see why he puts that on there later. And then this distance right here, we're going to call this distance d, okay? You'll see that this distance is important later. Here is DEM, which is the distance between the Earth and the moon. And here is DES, which is the distance between the Earth and the sun. So he's labeled all of this geometrically. He's going to see if he can he's going to see what he can figure out doing this. Now, if you look, you can see we got a lot of numbers we don't know. We don't know that. We don't know that. We don't know that. We don't have numbers for any of these except for the Earth, except for the radius of the Earth. So it's not looking good. It's not looking like we're going to be able to figure something out. But Aristarchus actually realizes that he can eliminate some variables here. The radius of the sun, or first, instead of talking about the distance from the Earth to the sun, what he can do instead is here he can just write 422 DEM. Because the distance between the Earth and the sun is just 422 times the distance between the Earth and the moon. So he can figure that out. So that's one less variable, basically. He's killed off this DES variable. Now, there's also another thing worth noting. The sun and the moon appear to be about the same size in the night sky, or rather in the sky. Both of them take up an angle of about 1/2 a degree. They subtend a 1/2 degree angle. They seem to be about the same size. But the sun is 422 times further away. So that means it stands to reason that the sun is 422 times wider than the moon. So he's able to write the radius of the sun right here in terms of the radius of the moon. It's one less variable. So things aren't looking too bad, huh? We've gotten rid of a few variables. How many do we have here now? We have the distance from the Earth to the moon, we have the radius of the moon, and we have this D right here. So we have 3 unknowns. Let's see what we can do. Let's see what Aristarchus can figure out. So the first thing Aristarchus ends up doing, well, here's the thing. I'm going to give you a simplified explanation of all of this math he ends up doing, but you can bet that it wasn't this clean when he first did it. He probably had to screw around with this for maybe months before this worked out. First, what he's going to do is he's going to find this distance D. He's actually going to figure out that he's going to eliminate that as a variable, okay? And now what is D? D is the distance from the moon, or the Earth's shadow, at the location of the moon. It's the distance between the moon and this point out here. So you might be wondering, like, what's the significance of this point out here? Well, first of all, it's a point in the geometric diagram. But in case you're wondering what like this point means, imagine if you're standing at that position. This is the position at which you start to see the sun poke out from behind the Earth. It's the point at which if you get to this point, the Earth is no longer large enough in your field of view to cover the whole sun. So that's what that point means, basically. These lines represent, the lines of the Earth's eclipse, basically. When you're in this zone, this is the darkness zone, which is a great video game, by the way. No, it's just a great video game title. I made that up. So that's looking good. Now he's going to try to find D, rather. And to do that, here's what he does. See this right here? It's a right triangle. And this right triangle has the same proportions as this big right triangle. Okay? It's because they all have the same angles, and Aristarchus knew this. And when you have two triangles that have the same shape, but one is just a scaled down version of another, you can write a proportion of the different sides. And so what Aristarchus writes is he writes the base of the little triangle divided by the height of the little triangle. What's the height of the little triangle? It's 3 rm, right? It's 3 times the radius of the moon, because this little triangle has a height which is that of the shadow's radius, okay, which is 3 times the radius of the moon. The base divided by the height of the little triangle is equal to the base of the big triangle divided by its height. Now, what's the base of the big triangle? This is a little complicated. It's D plus DEM plus 422 DEM, right? Because that's the base of the big old triangle. I'm going to draw that base. Look at it. Look at it. That's the base of the big old triangle, okay? And it's all of those things added up. What's the height of the big triangle? It's 422 RM. Okay. So this is actually not looking too bad. Look at this. We got RM on both sides. Those algebraically cancel. And then if you look, these two are like terms, so we can just add them up. So let's rewrite this equation with a little bit more simplicity. 422 DEM plus 422 DEM plus DEM is 423 DEM. Okay, so what he's done is, he's written this out. Okay, now he's going to multiply both sides by 3 in an effort to get rid of this 3 right here. Then he's going to multiply both sides by 422 in an effort to get rid of that 422 right there. Okay, we're just doing some algebraic manipulation. Oh, that 3 goes away. And let's look at what Aristarchus gets next. 422D equals 3D plus 1269 DEM. Okay, 3 times this here number. Turns out it's 1269. Okay, so let's continue our simplifications. We're going to minus, what happened? We're going to minus 3D from both sides. 419D equals 1269 DEM. Okay, now we're going to divide both sides by 419. And what this leads to is that D is approximately 3 DEM. The numbers come out pretty nice, it turns out. Well, at least I've rigged it so that the numbers come out nice, so we don't have to think about the crazy numbers. But this is what Aristarchus basically did. So we've eliminated a variable. Look at that. We've written this variable in terms of another variable. Okay, so instead of writing D right here, I'm going to write 3 DEM. Okay, we figured out that distance. So it turns out the distance from the Earth's shadow to this point where you start to see the sun peek out from behind the Earth, that distance turns out to be 3 times the distance between the Earth and the moon. It turns out that it's about that much, okay? So now, this is a lot of math. And what you can do, you can always rewind the tape, rewind it. You can always go back in this video and look and sort of refresh yourself with each step. Or what you can do, if those details aren't very interesting to you, you can just remember this. Aristarchus has drawn a geometric situation. And what he's doing is he's trying to take the thing, he's trying to eliminate variables. He's trying to write some of the lengths in this picture in terms of other lengths so that he's able to write a set of algebraic equations with the least number of variables. And this might allow him to solve for the size of the Earth and the moon. And it might allow him to do that because he actually knows the size of the Earth in kilometers. I've marked it. He actually knows the size of the Earth. And so he might be able to use algebra to figure out the size of the sun and moon. And that's exactly what he's about to do. He's going to write another proportion. This time he's going to compare the proportion of this little triangle here to this medium-sized triangle right here. Okay, let me show you what that proportion looks like. The base of the little triangle is equal to 3 DEM. The height of the little triangle is equal to 3 times the radius of the moon. Okay, let me remind you of that real quick. See, the height of the little triangle is 3 times the radius of the moon, and the base is 3 times DEM. Now he's going to set that up in proportion with the medium triangle. Now remember, all of these triangles are scaled up or scaled down versions of one another, so their proportions are equal. Okay, that's an important geometric fact Aristarchus uses here. So he's going to compare. So let's see, what's the base of this? It's DEM plus 3 DEM. So that means the medium triangle has a base of 4 DEM. And what's the height of the medium triangle? Well, the height of the medium triangle is just the radius of the Earth. So let's put that in there. And marking it to remind ourselves that we actually know that number. Okay, now check this out. Look at this equation he set up. Wha-bam! The size of the moon disappears. And look at this. Or not the size of the moon, the distance to the moon disappears. We now have an equation with just one variable. It's solvable. The 3's eliminate one another. Let me show you what we have now. The radius, 1 over the radius of the moon equals, let's draw that a little more neatly, 4 over the radius of the Earth. Let's take the reciprocal of both sides. The radius of the moon is 1/4 the radius of the Earth. And it turns out that this number is, now remember, we know the radius of the Earth. We know the radius of the Earth, so all we have to do is just divide it by 4, and we get that the radius of the moon is 1,593 kilometers. Now, this is not the exact radius, but in my story, I'm having Aristarchus get close. He is getting fairly close. I think the real number is more like 1,700 kilometers, something like that. So he's getting like decently close here. Okay, he found the but here. So here's the deal. You can see Aristarchus could have done this, and he did. His measurements weren't as accurate as I'm making them. But he figured this out. He figured out that the moon was roughly 1/4 the size of the Earth. Or well, again, I think his numbers were off. But he found that the moon was smaller than the Earth. And I gave you a particular number, which is not the number he got. But he found the radius of the moon. He finds the radius of the moon in kilometers. Now, remember, the radius of the sun is 422 times larger than the radius of the moon. So the radius of the sun is a gimme. It's just 422 times this number we just got. And that number ends up coming out to 672,141 kilometers. Now, this is staggering because it means that the sun is way, way bigger than the Earth. We can see here that its radius is roughly 100 times the size of the Earth, which means that the size of the sun is about 1,000,000 times the size of the Earth. That's how radius works. So this was mind-blowing to Aristarchus. He had no idea that these things would be this large. Again, he didn't get exactly this number, but the number he did get, it still made the sun way, way bigger than the Earth. And this was mind-blowing to him. And we're going to see that the fact that the sun is much larger than the Earth led Aristarchus to a startling hypothesis. But we'll get to that next, because Aristarchus is not done. He still wants to find the distance to the Earth. Or, I'm sorry, he still wants to find the distance to the sun and to the moon. So let's take a look at the next part of this. So again, Aristarchus, his motivation. Again, Aristarchus knows geometry's power to measure what cannot be measured. Oh no, that's the size. We already did that. Now that we know the size of the sun and moon, we might be able to use geometry to deduce more about the structure of the heavens. Specifically, let's see if we can get the distance to the moon and to the sun. Okay, so that's our question. Let's see if we can answer it. Now, the first thing I'm going to mention is that I'm going to remind you, the moon subtends a 1/2 degree angle in the night sky or in the day sky. What does that mean, to subtend the angle? So that means that if you measure, if you have a childish drawing, let's draw that more nicely. Oh, well. No, this looks better if I... My lines are so bad that Notability isn't even on board with it being a line. It's like, I'm not turning that into a line. You have to do better. So here's what that means. It means that if you measure an angle from one side of the moon to the other in your field of vision, it only takes up 1/2 a degree. Okay? And this is a function of both the size of the moon and how close it is. Imagine if the moon was closer. If the moon was closer, then maybe it would take up a larger angle in your vision. Maybe it would take up, if it was way closer like this, maybe it would take up 3 degrees. I don't know how big that angle is, but the bigger the object is in your field of vision, the more angle it subtends in your vision. So it turns out the moon takes up 1/2 a degree. Okay. Now, so what that further means is the following. Here's the way Aristarchus thinks about it. If you had 2 moons, then that would take up a full degree. 2 moons takes up a full degree, right? So if 2 moons equals 1 degree, then check this out. Let's say you times both sides of this equation by 360. 720 times 2 is not that. I don't know what I'm smoking. 360 times 2 is 720 moons equals 360 degrees. Okay, so what's the point of this? The point is that if you wanted to surround the entire Earth with moons, here's the Earth, if you wanted to surround the whole Earth with moons, sort of this circle made of moons, it would take 720 moons in order to do this. It's really crazy how... I'm not going to literally draw 720 moons. I don't got time. So here's his moon circle. There's 720 moons in it. Okay. And what Aristarchus does is he realizes, okay, well, I know the radius of the moon. So that means that 2 times that, let's see, 720 moons times the radius of the moon, or rather times 2 the radius of the moon. See, look at this. See, this is the diameter of the moon, which is 2 radius of the moon. 720 of those makes the circumference of the whole moon circle. That's the circumference of the moon circle, okay? Now, what he's going to do is he realizes that the circumference of the moon circle is related to the radius of the moon circle. Here's the radius of the moon circle, right? Well, the radius of the moon circle is just DEM. It's the distance between the Earth and the moon. So he can actually solve for the distance between the Earth and the moon using this moon circle. Using this moon circle idea. So let's work out the math. It's 720 times 2, which is 1440. 1440 times the radius of the moon is equal to 2 pi r. Because remember, this is the circumference of the moon circle, and that's the formula for circumference, right? Okay. Now, the r, so let's divide both sides by 2. So we're actually back to 720 rm equals pi times the distance between the Earth and the moon. Because remember, the radius of this circle is just the distance between the Earth and the moon. And we know this number, by the way. I should have marked this. We know the radius of the moon. We figured it out last step. So Aristarchus is going to use this. He's going to algebraically rearrange this. Let's take a look. 720 times the radius of the moon divided by pi equals the distance between the Earth and the moon. So by using this incredible abstraction of the moon circle, he's able to solve for the radius of this moon circle, of this circle made out of moons. And that gives him the distance between the Earth and the moon. Now, this makes a certain assumption. This makes the assumption that the moon is always the same distance away from the Earth, which is not quite true, but it's quite close to being true. And so as a result, it turns out that the moon goes in an elliptical path around the Earth, but the ellipse is pretty close to being a circle. So as a result, Aristarchus gets the right number. And actually, hold on, that's not what's important, because how did we get the right number to begin with, right? What's important is that Aristarchus had reason to think that the moon was always about the same distance away. The reason is this. The moon is generally the same size in the sky. You don't see the moon getting real big and real small. Now there is a measurable difference in size, but I mean, if he had measured that, he could have just taken the average size of the moon and done his calculations this way. Here I've shown in principle, you can see even with these details aside, this is how in principle you could find these numbers. And then honing them down to more exact numbers is just a matter of taking into account more details in the same way I've done here. So just because I'm dropping some of the details doesn't make the details that I have covered any less rigorous. Okay, so what does this number end up coming out to? What does this here number end up coming out to exactly? Okay, if we were to get a calculator out, then we would see that DEM, the distance between the Earth and the moon, is 365,000 kilometers away. 365,000 kilometers away. That's the distance to the moon. Okay? So, and what we'll see is that these distances end up helping Copernicus with his theories, but that'll have to wait till the next lecture. And as usual, thanks to Aristarchus's earlier discovery, we know that the distance between the Earth and the Sun is 422 times the distance between the Earth and the Moon, the distance between the Earth and the Moon, and so the distance from the Earth to the Sun is a gimme. It's just 422 times this here number. So let's write that number. Well, 154 million kilometers away. So Aristarchus discovers that the heavens consist of objects that are unthinkably large, that are separated by distances which are even more unthinkably large. The heavens are much larger than the Earth. He finds these particular distances. Okay? And this is the conclusion, and this is the last integration for this lecture. But before we finish, I'm going to tell you about some things that Aristarchus knew at the time. I'm going to tell you about some of the general things people knew in astronomy. People would notice over the course of the night that the stars would rotate in a 24-hour cycle. They wouldn't look like this, like you're getting, sucked into oblivion or something. What this is supposed to represent is the motion of the stars over time. This is done with a time-lapse camera here. But they would see that the stars moved in a 24-hour cycle in the same way that the sun did. Okay? Now, and so as a result, people would think that people basically thought, more or less, that the sun and the stars went around the Earth, right? It makes sense. That's what it looks like. And what was further known was that there were these special stars called the wanderers, or in Greek, planetae. Planets. These are wandering stars. And what was distinct about these stars is that they changed their position with respect to the other stars over the course of many nights. And so you can, even as the stars rotate, all of the stars keep their position with respect to one another, except for the planets, except for the wandering stars. And so it was supposed that these wandering stars also went around the Earth, but they went around the Earth in sort of a different cycle. It was also found, of course, that the sun has a yearly cycle in addition to a 24-hour cycle. And so they simply thought it was going around us in more than two paths at the same time. But that we're not going to get into that complication. But basically, here's what ends up happening. People generally think that the stars, the sun, and the planets are all going around us and that we are at the center, of course, because that's what it looks like. Except for the following. When you look at the planets in their, path that they take with respect to the other stars, they do this loop-de-loop thing. And if you use your modern knowledge real quick, you'll remember the planets aren't going around us. They're going around the sun. So as a result, it makes sense that they wouldn't follow like a straightforward circular pattern as they go around us. It turns out they do this loop-de-loop thing because of the geometry of the situation. Now, Aristarchus, of course, didn't know well. And so as a result, here's what Aristarchus ends up thinking. He says, maybe the sun is at the center, and the planets and the Earth go around it. That would seem to make sense, because look, these planets aren't going around us, because they do this weird loop-de-loop thing. So maybe they're going around the sun. And it would make sense if we were the one going around the sun, because we are so much smaller. Remember these numbers. Look at this. How big is the sun? The sun has a radius of 600,000 or 672,000 kilometers. We have a radius, the Earth has a radius of 6,700 kilometers. Let's see, what was it? No, 6,300 kilometers. We're less than 100th of the sun's radius, which means we're less than 1,000,000th of the sun's size. Why would the sun be going around us? That seems absurd. That seems like the tail wagging the dog. Like, imagine a dog wagging its tail, right? But imagine instead the tail staying stationary and then the dog going like this. That's absurd. That's not how things work. That's not how motion works. It would make more sense if we were going around the sun. And so Aristarchus, by getting a sense of the size of the sun and getting a sense of and getting a sense of these observations, was the first man to suggest that it's the Earth that goes around the sun and not the other way around. Unfortunately, Aristarchus faced major opposition, both from people who just weren't thinking about it too hard, but he also faced legitimate opposition. There was a very legitimate, wrong, but legitimate criticism. Here's the criticism. If we were going around the sun, then why don't we feel like we're moving? You can actually calculate, according to Aristarchus' theory, you can actually calculate how fast we're supposed to be going around the sun using this theory. And according to Aristarchus' numbers, we would be going around the sun at thousands of kilometers per second. Something like that. I didn't work it out, but really fast. So people are just like, well, if we were going that fast, wouldn't you be hanging on to like the nearest rock for dear life? And then wouldn't there be just wind blowing past you? So we can see that we're going to need to understand motion if we're going to get a further understanding of the heavens. And that's going to have to wait till next week for our next or that's going to have to wait till next week for our next lecture. And, what I'm guessing Aristarchus would have done is he probably would have stuck to this by saying, I feel like we wouldn't feel the movement somehow, but he wouldn't have been able to give some kind of way of arguing for this. He would just say, it seems like we wouldn't feel the movement because it's like consistent movement. But people will just be like, no, that doesn't make sense. You feel movement, Aristarchus. And so, again, we're going to see that a deeper understanding of motion is going to be required for our understanding of the heavens to evolve. And that we're going to see in our next lecture. Thank you for watching.